Hello students, welcome to this particular session. In the previous session, what we have discussed was regarding the effect of capacitance on the introduction of both conducting slab as well as dielectric slab. Students, we have discussed that on the introducing of a conducting slab or a dielectric slab, in both the cases, the capacitance of the capacitor tends to increase, right? Today in this session, what we'll discuss is when a dielectric slab is inserted or it fully occupies the space between the plates of the capacitor, and then we will discuss the variation of different quantities like what will happen to the charge, what will be the effect on the electric field, the potential difference, the energy of the capacitor, whether it will increase or decrease on the introduction of a dielectric slab, and we will discuss this scenario in two cases. When the plates of the capacitor remains connected to a source and when the external source is disconnected, right? So this is a very important topic, and we need to understand the concept first, and then we will try to complete this particular table, right? Basically, we will discuss the case where the dielectric slab entirely fills the space between the plates of the capacitor. We will discuss this under two categories: when the battery remains connected and in the second scenario when the battery is disconnected. We will discuss the changes which we will notice in these physical quantities: charge, potential difference, electric field, then capacitance, and then energy of the capacitor. So these are the two cases, 1 and 2. First case is when the battery remains connected and the dielectric slab completely occupies the space between the plates of the capacitor. And in the second case, the same scenario. Only difference is that here the battery is disconnected, right? So let's start. Let's try to complete this particular chart, right? Okay, we are aware of charge. In the normal scenario, charge, you are aware, is given by C into V. C stands for the capacitance, V stands for the potential difference. That's the relationship between charge, capacitance, and potential difference. Potential difference, obviously, it would be equal to Q by C using the same formula. Electric field. Now look, this is suppose the potential difference over here, and electric field is from positive plate to negative plate. And suppose D is the separation between the plates. Suppose D is the separation between the two parallel plates. Then electric field at a point is numerically equal to the negative of the potential gradient, isn't it? So here in magnitude, E would be given by potential difference divided by distance between the plates. In magnitude, it is V by D. The potential difference across the plates of the capacitor divided by the distance between the plates, right? So that is how its SI unit comes to be volt per meter. It is also Newton per coulomb, right? Capacitance, we are all aware, capacitance of a parallel plate capacitor is epsilon naught A by D. This is the original case where the space between the plates of the capacitor is filled with air or vacuum. Epsilon naught, it is the absolute permittivity of free space. Energy, there are various expressions for energy. Actually, there are three expressions for energy. One is half CV square, one is Q square by twice C, and the third one is half QV. So here let's write energy in terms of C and V. So it will be half CV square, right? So these are the basic formulas related to these physical quantities: charge, potential difference, electric field, capacitance, and energy, right? So one thing to be noted is that if the battery remains connected, as in case 1, this diagram is pretty clear. If the battery remains connected, battery means source, more than one cell connected, that is a battery, and it basically is a source of potential difference. So if a source is connected across the plates of the capacitor, then it will be able to maintain a constant potential difference, right? So when the battery remains connected across the plates of the capacitor, it will maintain a constant potential difference. So when the battery remains connected, then the potential difference it will be constant. It won't change. Right? It will remain constant. While on the other hand, if the battery is disconnected, definitely potential difference will decrease, isn't it? It is disconnected. Now, whatever charge is stored in the capacitor, now the path is incomplete. That is, the charge inside the capacitor, in a sense, get locked down inside the capacitor. Again, I repeat, as the battery gets disconnected, the charge remaining inside the capacitor get locked down inside the capacitor. There is no way that the charge can leak or charge can go or it can complete the circuit because of disconnection of this battery, right? So basic thing is, when the battery is disconnected, then the charge will remain constant. Charge will remain constant. These are the two very important facts. Again, I repeat, students, as long as the battery remain connected across the plates of the capacitor, it will be able to maintain a constant potential difference across the plates. So V would be constant when the battery remain connected. And as soon as the battery is disconnected, the charge will be constant because the charge in this case will get locked up inside the capacitor. It can't go anywhere, isn't it? The circuit is incomplete as the battery is disconnected. So the charge in a way remain locked inside the capacitor. So in that scenario, charge is constant at that instant. Clear? Also, one more thing. We have discussed it in the article, and to start with this session, we have already recapitulated that on the introduction of a dielectric slab, the capacitance increases. And if the entire space is filled with the dielectric slab, then the capacitance increases by K times. This we are already aware of. This we have mathematically verified, right? So whether the battery remains connected or battery is disconnected, it is immaterial. The capacitance of the capacitor will increase by K times, where K is the dielectric constant of the dielectric slab under consideration. That is, capacitance in this case will be K times epsilon A by D. So it will become K times C. That is, it will increase. It increases. C is the original capacitance. Now, when the dielectric slab is introduced and the battery remains connected, the capacitance will become K times. K is the dielectric constant of the slab. So in this case also the capacitance increases. On the introduction of the dielectric slab, the capacitance increases. Right? It increases K times. Look, over here epsilon would be substituted by epsilon, and epsilon is equal to K times epsilon naught. That is what I have written over here. So whether the battery remains connected or it is disconnected, on the introduction of the dielectric slab, the net capacitance increases. So K times the original capacitance. So it increases. No doubt regarding this. So in both the cases, the capacitance increases. So students, these are the basic facts which you need to know, and thereafter every other box can be easily completed, right? Applying simple logic. So let's start with this one. Okay, over here. Now V is known to us and C is known to us. Q is equal to CV. Now look, potential is constant. C becomes K times. So charge will also become K times. That is, it increases. Again I repeat, Q equals to CV. When the battery remains connected, then potential difference is constant. But capacitance becomes K times. So the charge will also become K times. So the charge increases. Now electric field. Let's complete this column. Now electric field. It's V by D. If potential difference is constant, and the distance between the plates of the capacitor, that won't change, isn't it? Obviously. So if V is constant, D is constant, so electric field will be also constant. What about energy? Now look, energy is half CV square. Look, new energy. It will be equal to half in the first case, first column. Half C. C means K times C multiplied by V square. V is constant, so it will remain same. So new energy will be equal to K times half CV square. That is, we will get K times new energy. So it will be K times initial energy. So it will also increase by K times. So is it okay? It's very simple, right? Let's consider the other scenario. Let's consider this one. Now Q is constant and capacitance increases. V is equal to Q by C. Now look over here. Q is constant and potential difference is Q is constant and potential difference is inversely proportional to the capacitance. Capacitance increases by K times means potential difference will decrease by 1 by K times. So in this case it will be 1 by K times V. Now since for any dielectric slab or any medium, the dielectric constant is always greater than 1, right? So therefore V by K would be less than V, original potential difference, right? So the potential difference decreases. It decreases. Now what about this one? Electric field. Obviously electric field is potential difference divided by distance. Distance between the plates will remain same. So whatever changes in the potential difference, the same change will be in the case of electric field as well. So the potential difference becomes 1 by K times, therefore electric field will also become 1 by K times. So therefore in this case the electric field would be 1 by K times. K, as I have stated, it is the dielectric constant of the dielectric slab. So 1 by K means the value of K is greater than 1. So E by K would be less than E. E is the original electric field, so it decreases. Last one, half CV square, that's the energy. Let's see. Okay, in this case the energy is to be found. So suppose in second case, half capacitance. Over here capacitance is K times V square. V is V by K. So V by K square. Right? So what do you get? Half K C V square divided by K square. So half CV square by K. Half CV square divided by K. So U double dash will be equal to 1 by K times the initial energy. Right? 1 by K times the initial energy. So students, what we get over here is energy would be 1 by K times the original energy. So obviously it decreases. So I hope now this chart is pretty clear to you all. Right? This is a very, very important chart. You need to know the reason behind each and everything. Right? So try to complete the chart logically using some basic concepts. So students, let's deal with some very important and conceptual questions. Let's try some numericals, right? So what to do is, listen to the question. Let us consider small spherical drops. And there are n type of such identical spherical drops, each of radius say smaller and carrying charge q. So what you are supposed to do is, if these n spherical drops combine together to form a large spherical drop, then you are supposed to find out the ratio of the charge, the electric potential, the capacitance and the energy of the big drop to the small drop. So I'll repeat the question. What I meant is, suppose these are n small identical spheres, n times, n identical spheres, each of radius r, and carrying charge q, and suppose each is carrying charge q. They combine together to form a big drop, say of radius r. Suppose the charge is capital Q, right? Let the potential across each smaller one be V, and over here it is V dash, right? Capacitance is C of each small spherical drop. Here the capacitance is suppose C dash. The energy of this small spherical drop is U, and the energy of the big drops obtained by the combination of these identical drops is suppose U dash. Understood now? So what we are supposed to do is, we need to find out the ratio of, first, ratio of the charge contained in the big drop to the charge contained in the small drop, right? Then potential or capacitance, C dash divided by C. Then third, we are supposed to find the ratio of the potential difference. And finally, we'll try to find out the ratio of the energy possessed by the big drop to the energy possessed by a single small drop. All in terms of N. We are supposed to get the answer in terms of N. N is the total number of identical drops, right? So this is a very, very good question, and it's pretty important from multiple choice questions point of view, and also from various competitive examinations, right? So let's proceed. You are aware charge is of additive nature, isn't it? And charge is conserved. So first and foremost, charge, obviously, if it is having n identical spheres, so total charge would be total charge of the system. It would be equal to Q plus Q plus Q n times. So total charge would be n into Q, right? This is total charge, and this is what total charge is concerned. So what will be the ratio? Q by small q would be equal to n is to 1. This is the first answer. It's simple. Just make use of conservation of charge, and charge being additive in nature, the net charge on the big sphere would be equal to n times the charge contained in the small sphere, right? No doubt regarding this. Now, in order to find out the ratio of the capacitance, students, we are aware capacitance of a spherical conductor is 4 pi epsilon naught r, right? So it is dependent upon the radius. So first we need to find out the relationship between capital R and small r, right? So volume of n small identical spheres would be equal to the volume of the big sphere. So therefore, n times volume of a small spherical drop. It would be equal to volume of the bigger one. So what do you get? 4 by 3, 4 by 3, it gets cancelled. N R cube is equal to R cube. Taking cube root, what do you get? N to the power 1 by 3. We'll make use of it. R by R is equal to N 1 by 3. Simply take cube root and you should get this result. Clear? So capital R by small r is equal to N to the power 1 by 3. So put this as A. We will make use of it. Now let's try to solve the second one. Capacitance of the big one. What is it? Capacitance of a spherical conductor is 4 pi epsilon times the radius. Radius of the big one is capital R. The capacitance of small drop, it will be again 4 pi epsilon small r. So what will be the ratio? Just divide these two. So 4 pi epsilon get cancelled. So we'll be left with capital R by small r. Therefore, C dash by C, it will be equal to R by R, and it is N to the power 1 by 3 is to 1. This is the answer of the second part, which is the ratio of the capacitance. Put this as 2. This is the answer of the second part. Clear, students? So now what to do is, let's try to attempt third one. The ratio of the potential difference. So let's try to attempt that. Now you know that V dash, it will be equal to charge, the constant with bigger drop, divided by the capacitance, C dash. And what about V? It will be equal to Q divided by C. So we need to get the ratio. V is equal to Q by C. We need to get the ratio. So on dividing these two, what we get is V dash by V. It would be equal to Q by Q and C by C dash. So let's get the result. Let's substitute the value, right? So capital Q by small bits, n is to 1. C by C dash, reciprocal of this, that is 1 divided by n to the power 1 by 3. Isn't it? So what do we get? N to the power 1. So base being same, the exponents will get algebraically added up. 1 minus 1 by 3 divided by 1. So V dash by V, it will be equal to n 2 by 3 is to 1. So this is the answer of the third part. So the ratio of the potential difference of the bigger drop to the potential difference of the smaller one, it will be equal to n to the power 2 by 3 is to 1. Right? This will be the ratio of potential difference. Students, last part is left, energy. Here we can make use of half CV square, isn't it? So let's do it. So energy, what we can do is, for energy, which is the fourth part, energy is half CV square, half U dash suppose, C dash, V dash square. And the energy of the smaller one would be half C V square. So let's take the ratio, U dash by U, it would be equal to C dash by C into V dash square divided by V square. C dash by C, it's n to the power 1 by 3. What is V dash by V? V dash by V is n to the power 2 by 3 is to 1 and square of it. So it will give us n to the power 2 by 3 is to 1 and square of it. Clear? So what do we get is n to the power 1 by 3 multiplied by n to the power 4 by 3. So U dash by U, it will be equal to n to the power 5 by 3 is to 1. So this is the answer of the fourth part. So students, do remember these results. In MCQs, you can make use of this result directly. N is the number of drops, which may be 8, 27, 64, and accordingly substitute the value of n and you should get the ratio of various physical quantities: charge, capacitance, potential and energy. Right? So this was a very, very good numerical. We can discuss one more numerical actually. We can discuss the equivalent circuit for an infinite grouping of capacitors, right? We'll make use of GP over there, geometrical progression. So let's try to attempt that numerical as well. So question is, there are all identical capacitors, each of capacitance C, and they are connected as shown in the figure. I'll draw the network, and we are supposed to find out the equivalent capacitance of the network. We are supposed to find the equivalent capacitance of the network. So this is the diagram basically. This is point A, and these are the capacitors connected, all of equal capacitance. Let's say C. In the first branch, there are 2 capacitors connected in parallel, or there are 4 capacitors connected in parallel like this. In the next, there will be 8 capacitors. So you can easily check the grouping: 4, 5, 6, 7 and 8, and so on, and so on. So this is point B. What we are supposed to find is, we are supposed to find out the net capacitance between the points A and B. We are supposed to find out the net capacitance between the points A and B. Each capacitor is having the same capacitance of C. Each capacitor is having the same capacitance of C. That is, I'll write like this. Here 1 capacitor connected, here 2 capacitors are connected in parallel, 4 capacitors are connected in parallel, Here 8 capacitors are connected in parallel. In the next one there will be obviously 16 capacitors, then 32, then 64, then 128, then 256 and so on. It's an infinite network, right? So let's try to evaluate it. It will be C. These two are connected in parallel, so resultant will be 2C. Here these four are connected in parallel, it will be 4C, then it will be 8C. Then in the next one where 16 capacitors are connected in parallel, it will be 16C, then 32C, 64C and so on. Now all these are connected end-to-end connection. So they are connected in series. The charge across each of these capacitors will be constant. So they are connected in series. And in the series grouping, the formula is 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4 and so on. So 1 by C can be taken as common. The terms can be rearranged in this manner, isn't it? 1 by 4 will be common. It can be written as 1 into 1 by 2 to the power 2. 1 by 8 may be written as 1 into 1 by 2 to the power 3. 1 by 16 may be written as 1 by 2 to the power 4 and so on. Why I have written in this manner is because it is in the form of GP. Remember, the first term is A, the second term is AR, third term is AR square, fourth term is AR cube, fifth term is AR to the power 4 and so on. A is the first term, which is 1. R is the common ratio, which is half. And remember, this is an infinite series of geometric progression. And sum to infinity of a GP, the formula is A over 1 minus R. So here what we get is A is 1. 1 minus common ratio is half. So what do we get? Half, 1 divided by half, that will give us 2. So the value of this entire term which is inside the bracket is 2. Therefore, 1 by CAB is equal to 1 by C, and the value of this entire term inside the bracket is 2. Therefore, taking reciprocal, what we get is CAB is equal to C by 2. So this was again a very good question, right? So students, I hope you have understood all the concepts whichever we have discussed today, and please, as I have always maintained, please do believe in your abilities and try to study on consistent basis, right? Don't lag behind in syllabus. Keep working on your drawbacks and try to strengthen your strengths, right? All the very best. We'll continue in the next session.